So now I will present the MARLIN paper, which is our recent publication at P-POP conference this year. Uh, this work is done together with Elias, Roberto from our group, and Torsten and Dan. Uh, so for the introduction, uh, so this is some background information about large language model inference. So as you can see from this plot, the model sizes are growing exponentially with respect to the time. And the recent models have shown the good performance on some daily routines. As the example you see here, many of you have used it. Um, However, to make the models running more efficiently, we have some compression techniques, namely the quantization and sparsification. And there are also some hardware support on the modern GPUs. And this work aims to provide some uh, framework to adapt the compression techniques to the hardware supports. So as an illustration, the most recent NVIDIA GPU supports some quantized data formats, like what is shown here, and also some sparsity matrix formats, such as this 2-4 sparsity tensor cores. And the tensor core is shown on the right side, which can do the matrix multiplication more efficiently. The motivation of this paper is that we found out that the batch scenario, which is batch inference, uh, is a key use case in the LLM inference task. For example, OpenAI claims they have 100 billion words per day, which means there are a lot of opportunities for the parallelism in the token generations. Um, and the existing kernels, I mean the kernels before this paper, are mainly focused on um, the backside of one, which means they only focus on to influence one token per time, and they are not actually targeting the batched influence use cases. Um, so they don't perform good or achieve the optimal performance in the batched inference cases. Um, However, after our calculation, we found out that if we can achieve the theoretical best performance, there could be at least about four times speed up based on the GPUs that we currently have. So now let's introduce our paper, which is called MARLIN. And in this plot, I show the typical use case of our kernel. So we have a big matrix, which is quantized to int4, and this represents the weight matrix in the fully connected layer. And there is some input activations, which is here called A. It has some small batches. The size is usually not large, say for example 16, 32, or 64. And the output matrix is C, which is also have the same shape as A, or similar shape as A. There are three main challenges for this paper. So the first is we need to carefully configure the parallelization levels, um, which means we need to ensure that loading the context the matrix A is actually the main runtime bottleneck, not to repeatedly load the smaller matrix A. Um, and the second one is the as runtime is dominated by memory loading. So we have to ensure that the memory loading hits the peak efficiency. And the third one is for medium M, the cost of maximal computations and the memory loading almost have the same cost. So we need to be more careful in this use case to ensure that it's not memory bound or compute bound, and they are somehow achieves the balance. So what I talked for the last one is actually referred as here. So for Backstack 64, it's kind of at the border of memory bound regime and the performance bound compute bound regime. So we need to be more careful at this point. There are several key aspects in the kernel design. Um, Yeah, by the way, our kernel targets for the int4 times FP16. There are more formats exist now based on our kernel or inspired by our kernel. But let's just focus on these two data types, and the output is also FP16. So one of the key design is that we need to firstly bound by weight loading, not to bound by loading other components. And we also have some we also design some groups to partition the matrix into different blocks and let each streaming multiprocessor or ISM in the GPU to handle each of the sections. And here our emphasis is we need to hide the bandwidth cost of the loading A, not within the L2 bandwidth. And also we need to partition C and other matrices accordingly. So a second aspect of our kernel design is we need to maximizing the loading bandwidth. So here, for example, we have some instructions to load or evict the L2 weights. And the third one is memory loading pipelining. Well, I think you can see from here that this the horizontal line is the time, and the vertical line is the steps. So at the time, at the at the beginning, we just load the first block, and at the second time, we load the next block and also do some computation on the previous blocks and so on, so that after this pipeline, all the components in the GPUs are fully utilized. And we also introduce this kind of struct partitioning because our batch size from the input and output are relatively small, so that we want to have more equally balanced partitioning. Instead of doing the naive partitioning across columns, we also have this kind of partitioning that connects different columns. And this one ensures that all the streaming multiprocessors have roughly the same distribution workload. And we also have some other tricks on the dequantization and the tensor costs and so on. So now let's also introduce the sparse version of MARLIN. So we also decide to support the two-fold sparsity on this kernel. By two-fold sparsity, we mean that we first do some so by pruning, we mean that we set some of the weight to 0, which results in this kind of sparse pattern. and we can execute this sparse matrix multiplication using our sparse kernel and on the sparse tensor cores. The sparse kernel takes the compressed data formats of the weight matrix and do the computation based on these compressed formats. So for the evaluation parts, this one is for the layer-wise performance measurements. We take the shape of these popular models and we benchmark on these kind of shapes and average using because each model has some different shapes, so we take the average. We can calculate the speed up that we see our model achieves about 3.5 speed ups to up to 4 times speed up on different models and different GPUs. We also benchmark particularly on this 72K times 18K shape, which is optimal for our design, so that you can see we achieve about 4 times speed up for the dense version, and also about 5 times speed up for the sparse version of MARLIN. Regarding the accuracy, so accuracy is not our paper, but we still want to show that the data format that is supported by our kernel is actually useful in the real quantization scenarios. So here we show several benchmarks, and the int4, which is used by MARLIN, is very close to the FP16 full precision baseline. For the sparse version, because we also do some fine tuning, so the accuracy is actually slightly better than the baseline. We also have some end-to-end results on the inference speed. On this plot, we show that the batch inference is accelerated by about 3 times. There is also a popular benchmark called time per output token, TPOP, which essentially measures the latency between different tokens. Here we show that the MARLIN achieves about 2.8 times speed up, and the sparse version has 3.3 speed up to reduce the latency across different polling intensities. And this work is already open source on the GitHub of our group. Yeah, and that's all. Thank you.